Okay, today we're going to be talking about kinetic energy and looking at kinetic energy in a given sample. So, if we can take a kinetic energy and we graphed it, kinetic energy of a sample, so we took each and every single molecule of kinetic energy and we graphed it, we get a graph that kind of looks something like this. So what we see here is a sample of any kind of substance, and what we see is if you had one sample, each molecule is graphed. So here's a kinetic energy, what we call a kinetic energy distribution graph, and what it is that there is each molecule is represented. So most of the molecules have a kinetic energy on this particular graph of 400, 380 or something like that. Anyways, and there's a few molecules that have a really high kinetic energy and a few molecules that have a really low kinetic energy. Okay, but the majority of the molecules have a kinetic energy that's between 300 and 500. That's the majority of the molecules. So what is temperature? Well, temperature is just a measure of the average kinetic energy. So if you had to take all of these kinetic energies and find the average of them, that would be your temperature. So some of them have a really high number and some of them have a really low. The majority of the molecules are in the middle. So again, temperature is a measure of the average kinetic energy in a sample, and if we were to take the average of all of these molecules, the average would look something like this. Okay, this would be about the average. Okay, and the average is usually quite close or pretty much right at the peak of a distribution graph. So which one would have, here's two different samples. We have this blue line sample and then this red line sample. And what a lot of students get confused on is like they think that this blue one has a higher temperature. But if you remember, kinetic energy is temperature is the average kinetic energy. So if we were to take this and find the average of this red sample, it would fall somewhere close to the middle here. And same with the blue sample, it would fall somewhere close to the middle here. So here is the average kinetic energies of the blue sample, which is right about here, and the average kinetic energy of the red sample. So as we see here, this one is farther forward, so this one has a higher temperature. Why is this so much higher? It just means it has more particles with this lower kinetic energy. Or in other words, since it's a lower kinetic energy, it is a lower temperature. Okay. Now, we want to answer a question like, why do temperatures mean increased reaction rates? Well, more molecules have sufficient energy to collide with one another. So here is a graph of something with a low temperature. So as we see that nice high peak right there, that's really far towards the left, and up on this side right here is the amount of particles, and this right here would be the amount of particles with enough kinetic energy. So as we see here, only a few amount of particles have enough kinetic energy. These particles right here, shaded in gray. Now, if we had one that had a higher temperature, now we can see that the higher temperature has a greater amount of particles with sufficient energy. So what this means is is that this line this is enough energy for a reaction to happen. So this new graph that we have, this one right here, this has a higher temperature, and if we can see the amount of shaded gray area, it has many more particles with enough energy for a reaction to happen. So it has enough, it's essentially like having a higher concentration. More molecules are going to be hitting each other, and they're going to be hitting each other with enough energy, and reactions are going to happen. Now this one with a lower temperature, reactions are still going to happen, but there's so much less particles that the reaction is going to be lower. The reaction rate is going to be lower. So what we can say is what chemists and scientists have come up with is a basic rule, and we have come up with a thing that says for slow reactions, and again we need to emphasize slow, for slow reactions an increase in temperature by 10 degrees approximately doubles the reaction rate. So here we have two different samples. So the blue one and then the red one, and the red one is a sample which is about 10 degrees warmer. Okay, and so the reaction rate doubles. So here is the amount of here's the cutoff point for to see if a reaction is going to happen. So all the particles over here have enough energy that a reaction is going to happen, and the area underneath the curve is about twice as much underneath the red curve than it is the blue curve, and that means the reaction rate is going to be twice as high for the underneath the red one, for the red sample, compared to the blue sample. So as we wrote here, although the energy of most of the particles hasn't increased much, there's a large increase in the number of particles with energies equal to or greater than the activation energy. So the area under the curve has approximately doubled when temperature is increased by 10 degrees. And again, this is our cutoff point, so everything on this side of this line, has enough energy to react. And for the blue right here, we have maybe this much area, but for the red we have, even though it doesn't look like much more, but the amount of area that we do have is about double, because it includes this and all of this. So here's the red area, and it's about twice as much as the blue area, and therefore since we have essentially doubled the amount that can react, we have doubled the reaction rate. Now I want to look at how reactions happen, and more importantly, why reactions happen. So if we take like a reaction like something simple like CH4 plus O2, and this is a combustion reaction and makes H2O and CO2. Now this reaction releases a lot of energy, it's very exothermic, but this reaction just doesn't spontaneously burn. So this is a burning reaction. It's a combustion reaction, but if you had methane, or in other words CH4, it doesn't just burn by itself. Okay, it needs a little bit of a kickstart. It needs what we call a activation energy, a certain amount of energy for this reaction to actually go forward. And how does it get that energy? Well, we know it gets that energy from when kinetic energy and from molecules moving around and colliding with one another. And so how does two particles colliding with one another create enough energy for a reaction to happen? And we're going to look at that next. So what we see here is two particles, and they're going to start to come closer to each other. So the particles start to come closer, and as we see, when the particles come closer to each other, their potential energy starts to increase. Okay, so reactants have kinetic energy, they're moving closer to each other, and when they start to come closer to each other, about to collide, the electrons start to repel. When the electrons start to repel, the particles are going to get closer, and therefore the particles are going to slow down. So we see them slowing down, and they're coming closer and closer, and the potential energy still increase. So it's slowing down. So in other words, kinetic energy is converted, kinetic energy is changed into potential energy, and they even slow down even more. So they start to go really slow, and then that's when all of that kinetic energy has changed into potential energy. And then they collide, and they're full of a lot of potential energy, and they're able to then react. So what we see here, this is what we call an activation energy. So here's our activation energy, and all it is two particles coming closer and closer, and just like that graph showed, their potential energy goes up. Okay, so the potential energy goes up because particles right here, we're having kinetic energy is changed into potential energy. Okay, so we have molecules are moving around, they have kinetic energy, and then they start to come and they're about to collide, and kinetic energy is changed into potential energy. So since it's a potential energy graph, the potential energy starts to increase. Now it gets to a point right here where it's at the top. It has so much potential energy that it's very, very unstable, and we call this point right here, this point, we'll do it in blue, we call this point right here the activated complex. So kinetic energy is changed to potential energy, and the molecules are full of potential energy, and we have this really weird arrangement, and it's an arrangement of atoms which are between reactants and products. So on this side we would have reactants, and on this side we would have products. So reactants are going to turn into products, but before they do, they turn into the activated complex. The activated complex, they only stay as the activated complex for maybe 1/10 of a second, and then they quickly change into products. Okay, they're very, very unstable. The reason why an activated complex is so unstable is that it has a high amount of potential energy, and it wants to reach a more stable state, and it releases a whole bunch of potential energy, and it comes back down and changes into products. And so in other words, potential energy is then changed back to kinetic energy. Okay, it's too unstable. There's too much potential energy here, and potential energy is then changed into kinetic energy. And this is how a reaction happens: is that it has to come together, and then change into products. And this is why things like CH4 and O2 just don't change into water and CO2 by itself. It needs a little bit of energy to happen. Same thing, any kind of exothermic reaction, say if you had paper burning, paper just does not burn by itself. Paper needs a little bit of energy, and then it can change into products. Okay. Next time we're going to talk about the relationship between potential energy and kinetic energy, and how those two graphs are related.